Hello, everyone. I'm Eric Hyam, Technical Editor with Microwave Journal, and thanks for joining us for the latest Microwave Journal online panel session. We've got an excellent session today on a topic that I'm sure is near and dear to everyone. Today's panel session is entitled AI and RF, and we've got a great panel of experts with us today from Keysight EDA, Miller MMIC, Cadence Design Systems, and MathWorks. So this will be an interesting session. So let's get started. And I'd like to do that by spending a few minutes framing the discussion with some thoughts on the topic. So I think it's important to start with the market. You know, what's the reward for all the industry's hard work? And as you can see from this slide that averages a number of market forecasts that I could find on the internet, that reward is large. So roughly 32 billion in revenue last year, growing to 100 billion in 10 years. And that's RF components, so passives, semiconductors, connectors, etc. But as they say on the infomercials, but wait, there's more. So in this slide, I've opened up the viewfinder a bit to include all semiconductors, and primarily that includes silicon and non-RF functions. So this number gets reported pretty widely, and as you can see, it's even larger. So semiconductor revenue is expected to grow from about 610 billion last year to surpass $1 trillion around 2030 and hit 1.34 trillion in 2034. But again, there's more. And in this case, the more is the electronics industry in its entirety. So if AI lives up to the promises, it will have implications for the entire electronics industry, and those numbers get even larger. So that market reached $4 trillion in 2024, and it's expected to grow to almost 8 trillion in 2034. So if those forecasts are correct, the RF opportunity will be 100 billion in 2034, but the electronics market will be about 80 times larger. And as the slide says, there could be even more. So what's that? Well, services. When some enterprising marketer or forecaster ties in the service revenue from services that have improved or expanded because of AI or wouldn't exist without AI, those numbers will get even larger. So I thought this was interesting. I asked ChatGPT to kind of self-report and not be bashful. And this is a partial list of all the things ChatGPT says AI can do in the RF space. And I won't read them all, but you can see it's quite the laundry list of accomplishments: design, optimize, predict, improve, enhance, innovate, etc. So arguably, AI could increase the slope of an RF component market slated to hit 100 billion in 2034 as part of an electronics market exceeding 8 trillion. So very large stakes and very large incentives. But the key to any forecast is execution. And we've got a great panel of industry experts here from companies that are working hard to enable all these market segments to get a lift from AI. So let me start by getting the panelists to introduce themselves along with a short description of the companies. And let's go in the order of this slide. And we'll start with Alexander from Keysight EDA and go down the list from there. So Alexander, if you don't mind getting us started.
Thanks, Eric. Thanks for having us. Great topic. My name is Alex. I'm the Senior Director in Keysight EDA, serving as a portfolio manager for RF microwave, power electronics, and device modeling. As such, I'm also involved in a lot of AI ML initiatives we are driving to enhance those solutions, especially on the digital side of things. But since Keysight is also a hardware measurement company, we also have the physical thread. As you highlighted previously, there's a big domain to cover, which could also have measurement insight for RF.
Great, thank you for that, Alex. And Edward?
Yeah, hi. My name is Edward Heidebrecht, and I'm the CTO of RapidRF, the AI platform. And before RapidRF, I worked as an RFIC research engineer at the Aachen University in Germany, where I also did my PhD. And during that time, my research focus was on RFIC architectures and also including architecture for integrated door decoy amplifiers. but also one of my focuses was the design automation of RF circuits. And now with RapidRF, we are pioneering the automated design of RF circuits, and by that drastically reduce the overall design time, minimize the costs, and also quality of automated circuits. And soon, also our customers can benefit from our AI platform.
Great, thank you. Michael?
Hi, Michael Thompson with Cadence Design Systems. I'm a distinguished engineer in the Virtuoso R&D group, and I was originally the Virtuoso RF solution architect that developed our RF solutions. We are now extending that into heterogeneous integration and wrapping our artificial intelligence applications around that.
Excellent, thank you. And last but certainly not least, Human?
Hello, my name is Human Zarenkub. I am the principal product manager of all the wireless communication products at MathWorks. MathWorks been a long-term presence in the engineering and scientific community. Lots of students learn with MATLAB, our main product, and we have developed lots of standard-based wireless communication products, matching different standards in the industry, 5G, LTE, satellite communication, and so on. And I am responsible for those products, as well as the new area of applying AI techniques to solve wireless communication. So that's my responsibility at MathWorks.
Excellent, thank you, Human, and thanks to everyone for those introductions. So let's dive into the question. And kind of on a broad scale, on a society scale, people seem to be getting used to AI, but that awareness looks to be based on large language models and generative AI for text, videos, and images. How is AI going to be helpful in RF applications? And maybe let's start, Human, with you.
Yeah, in terms of the applicability of AI methodology to the topic at hand, the RF, our customers, and we believe that AI methodology is an alternative methodology to the existing traditional approaches. So it augments and improves on that, meaning that traditionally in the world of engineering design, you start based on basic principles. You model your system of interest, the input, the output, the states, and then you add parameters and you express the model, and then you build a physical device that matches that. Now, we think that AI is essentially data-driven, meaning that instead of you put most of the onus on the modeling simulation based on finding the right model, the data will actually inform the model. So, the area that we see our customers trying to apply AI essentially in three areas where the traditional approaches have been lagging, the AI is showing its promise. And those are nonlinear problems, multivariate problems, and the problems that incur lots of computational complexity. So people are taking those problems and applying AI methods, and we see this dance going on as a complementing approach until AI can take over, and we don't know when that will be. So that's the area that we see the AI in our RF portfolio, not essentially on the large language model, but on the applicability of those types of problems.
Yeah, excellent. Michael, how about from the Cadence standpoint?
From the Cadence standpoint, we see AI in several different areas that we've both implemented and we're working on implementation now. Certainly from the LLM standpoint, there are lots of applications we're looking at, and you'll probably see some of those things released later this year. But as you know, Virtuoso is kind of the workhorse for analog RFIC design. And it's a very powerful, very capable tool because it was meant to completely build ICs. So we have to worry about implementation and verification, lots of things. And there's a lot of customization you can do in Virtuoso, and often just knowing those commands or how to do that customization can be very difficult to find because it is so powerful. an LLM that you could ask it, hey, I need to do this function. Can you tell me how I need to go about it? Could you write me a simple skill script to do that? Those types of applications are just enabling the engineer to move faster. Things they would have to go out and research on their own can be done quite easily with an LLM. So we're certainly looking at applications like that, as well as when you're going to run a simulation, test bench setup is it takes time. Even if you're copying an existing bench and setting it up, there's quite a bit of work that has to be done there. If I could simply tell a LLM to go grab that test bench I used before, modify it for this reason, and give it to me. Again, these are just productivity saving things that we see as low hanging fruit in the Virtuoso environment.
Great, thank you. Alex, from the Keysight standpoint. Alex, I think you're muted.
Thank you. Yeah, similar to what we heard before, in Keysight, our design software ADS is a complex, very powerful solution. And we have a couple of areas where we see AI will be useful. I think the keywords here are augmentation, enhancement, and support, right? The LM domain, which Michael just outlined, will basically enable engineers who are less experienced with the tools or even with the design process to use those and basically augment their capability, their skills to just accelerate their designs by using the tools or by using certain techniques they were not familiar with. So it's a question of chatbots and potentially co-pilots who can drive the solutions. The other piece, the augmentation of the data set. So the data-driven approach is basically a way to move away from physical-based models, which took a long time in the past to understand and develop. Now you have a technology where you can basically just feed high-quality data and get right away models who represent the performance of those systems. So we see this in surrogate approaches. We see this in, you could also say, black box modeling approaches. It just pushes the requirement of high quality into the data domain, away from the physical model description domain.
Great, thank you. And Edward, your perspective is a little bit more from the user standpoint, I guess, where you may be a bit more product centric, and I don't mean that in a bad way, certainly. But so I mean, how is that making your life easier, and how is that working with your company?
So I basically have to add up to what my colleagues said in here. So AI will definitely go way beyond than just a simple assistance tool, I think. So from rapid RF perspective, AI is basically able to completely automate entire RFIC circuits and up to tapered ready designs, and by that also will bring a so we will see that customers will get perfect. So this revolution, we believe that will also enable to one problem we are seeing ever increasing talent gap that we are seeing.
Yeah, thanks, Edward. And we're having a little bit of trouble with your audio. But so kind of related question, the next question. So we just talked a bit about kind of at that 50,000 foot view, I guess. How are you implementing AI? Can we get a bit more specific, and how's what you're doing? How do you see that benefiting the RF and electronics industry? How's it going to enable those market forecasts that I kicked off with?
Well, I would say one thing that it's going to enable is the productivity increase. So we're always seeing that we need more functionality, we need smaller die, we need to pack everything tighter and tighter and tighter. And as we do that, we want to jump from one node to the next, one node to a smaller node to increase functionality and to decrease the area of the die. but often you're using the exact same design. All you want to do is you want to go from 28 nanometers down to 22 or whatever. So we have a process where we can migrate that design with AI from one node to the next. We use recentering to recenter that design optimization essentially. And then we can even develop layouts based on the original layout or new layout. So it's kind of something that an engineer would do by hand, but it's not that I'm redesigning something. I'm just moving it over a little bit. So it's a very defined problem. But it takes a long time if you have to do it by hand. And here's a lot of things that AI optimization, generating layouts automatically and doing routing and the sort of the guts of actually getting the design done can be automated. That's one area Cadence is looking at and has active products that do those things.
Yeah, from our side, I would add there are basically four general directions. Lowering the barrier for inexperienced people to get into RFIC design. RFIC design is still quite often seen as an art more than anything else. So it's a quite steep learning curve. Even when you come out of university, you're still learning. So enabling people to be faster, more efficient, increase productivity is certainly one of the main goals here, right? The other thing is similar to what Michael was saying is optimizing the circuits. That can be from technology node to technology node, but it can also be along the RF specification. So if you want to change the frequency, if you want to change the bandwidth, if you want to change the power of a circuit, you can do specification-driven designs using AIs. If the AI understands the system and knows what can be modified, or starting from a white piece of paper, going into inverse designs where you just give a specification to AI, are areas where we will see AI being applied. And in that last domain with the specification-driven approach, you will also see that AI will come up with solutions which engineers might not have thought of. So we're talking here about generating unique or non-intuitive RF designs. There are a couple of papers out to talk about weird matching networks or resonators and other things which can be basically generated, which a human wouldn't have designed.
All right, excellent. Anyone else want to chime in on that?
I can add a little bit. Our customers for MATLAB and its products, they model and design wireless systems, including RF, and they implement on the hardware and they test it. So this is an end-to-end workflow. And the application of AI, essentially what we have for them is the ability to dive into detail of AI, neural network model, machine learning, reinforcement learning, so on, understand essentially the underlying principles of that, apply that, and then the integration of data with that. So MATLAB has lots of connectivity to sources of data, and physical data, augmented synthetic data, and so on. So that is what we provide. We provide insight into not only the algorithms that are components of various systems, the digital baseband system, the RF system, the antenna system, and overall system design, but also the foundational aspects of different neural network models. We have multiple products, the reinforcement learning toolbox, deep learning toolbox, and so on, who gives you insight into what it means to have different models, parameterization, and how you apply data to train those models. So it's more about a foundational approach to the task of learning how to apply AI techniques to your RF systems.
Great, thanks, Umman. So in kind of what I guess I'll call the snake eating its tail question, we've talked about kind of how products and capabilities are enabling others to use AI. How is AI contributing to your product success? Are you using AI to generate your AI kind of driven products? And if so, how? So maybe Human, start with you on that one.
So yes, so because we have this foundational AI software tools, I mentioned multiple of them: the deep learning, reinforcement learning tool, and machine learning. Essentially, toolboxes. Toolboxes for us in MATLAB is a bunch of algorithms that set into motion the mathematical operation of these entities. So we use our own toolboxes, the deep learning toolbox, reinforcement learning toolbox, to and apply different applications and apply those tools to come up with AI-based solutions. For example, one of the areas that we tried to test our AI methodology is the problem of digital pre-distortion in RF design. We all know that power amplifiers have nonlinear characteristics. The 5G and 6G and so on will require large bandwidth. If your bandwidth is very large, we're talking about gigahertz bandwidth, the nonlinearity will substantially affect your performance. So you have to combat nonlinearity of your circuitry with digital pre-distortion. And it's a nonlinear problem. And we apply those AI techniques in order to find better optimal solutions than the classical solution based on interpolation, other techniques. So this is how, and then we compare the results we get from AI methodologies with the one that are based on classical techniques. So that's how we create these things called examples or design patterns for our customers to see how AI in action will beat by how much the traditional approaches to same design problem. That's an example of that. Yeah.
Yeah, great, thanks. And I like that AI in action term. Alex, from the Keysight standpoint, what are you folks doing? How internally are you using AI to help the industry advance AI and use AI?
You're muted.
Thanks. What Haman outlined is also one of the vectors we're going after. So just having this kind of capability in one of the product lines is certainly an area how we use the technology. In addition, I would say there are a couple more. One is you can actually use AI in the simulator itself. So there are technologies which you can apply to just accelerate the simulation by itself. So that's visible in EM, FEM simulation and SPICE simulation and system level simulations. So there are model order reduction technologies which have been also shown in papers, accelerations beyond a factor of 1,000. And that just kind of allows you to look at larger problems. So we are now basically also expanding the dimensions you can optimize rather than having 4 or 5. We're now talking about 30 or 100 dimensions you can potentially optimize. That's the other area, right? Optimization. So optimization can be significantly enhanced using AI. There are, again, different technologies which we are investing into. And just as a long-term vision, enabling inverse design approaches similar to what Haman mentioned is like a system itself has many components to it. In the past, you did specification for each component at an architectural high level, and you just hope that the systems will perform as specified. But in reality, if you go into the lab and you measure the solutions, you will always find there's a delta, right? So there's a certain amount of correction you had to do in the past in iterating through your product design. AI enables you to basically, in the design phase, to manage and resolve some of those inefficiencies in the design. So you're not just specifying models anymore. You try to drive it from a final system level specification all the way down to the smallest component. And since we now can tackle higher dimensional problems, you can basically optimize all at once. So it's a complete system solution enhanced through simulation technologies, which are significantly faster, and AI is able to grasp higher dimensions. So it's a combination of all of those tools plus the augmentation of the engineer to basically enable him now to drive those even more complex solutions and design tools through chatbots, co-pilots, is basically a big mixed bag of using AI in RF.
Great, thank you. Michael, your thoughts?
Yeah, so a lot of what's been said, certainly we're doing, but I think as we go forward, what you'll start to see is there'll be a lot of vanilla solutions, but you want to be able to customize it for your particular applications, your particular company, and your particular experience. So what we've offered, added to some of the other things I already mentioned, is the ability through advanced optimization cockpit that we have. I can add my own machine learning or AI applications. And a very good example of this that was published or you can find press releases on was MediaTek used this to build their own machine learning algorithms that they integrated into Virtuoso that allowed them to migrate an entire family of oscillators, recenter those, and take advantage of previous test data and previous learning in that ML application to generate this new family of oscillators. But it was all their own IP. They kept it in-house, and they were able to train and use the tools to do something that was significantly different for them and creative.
Yeah, that's interesting. Thank you. And Edward, let's see.
Yes.
Hopefully we've got your audio fixed. And what are your thoughts on this?
Yeah, let me know if the better now. Can you hear me?
So far, you sound a little bit better.
Okay. Okay, good. Because at the very beginning it was quite fine, I think. So maybe I would compliment to the very beginning and get to you. So at Rapid, I've already basically developed an AI-based platform that's already able to completely design automatically RF integrated circuits to tape-out ready design. And, so in the case of Rapid RF, here leveraging AI, and so basically orchestrating the generation of circuits and concepts that the customer or the user is basically requesting, and then also doing a much more refining of the circuit. So this is already the case at Rapid that is taking care of it. And also in addition to that, answer from before, we're going to the data-driven AI training. So in our case, our AI is already performing continuous line exploration. That means for various kinds of and that refinement is already capable of learning and improving its future requests.
Good, thank you. And so I think that here's a question that came in from the audience, and I think it fits nicely here. And I think Edward touched on this a little bit, and it's kind of gets to the heart of this whole panel. How far are we away from the goal of telling AI technology or telling AI the technical requirements and then AI generating the design? How far away, or are we there already?
Maybe I can take this first.
Absolutely.
So I think in comparison to the other areas where you see AI emerging, and some of those, especially in the LLM domain and the chatbot domain, came really rapid, right? We have to acknowledge that RF is a data scarce domain, and you need a lot of data to train AIs, right? So that may explain a little bit why it feels like we are lagging behind, but in reality, RF is not like digital or like doing a web crawl, they can just extract billions of parameters, or where you have really well-refined rules and tools which can be used to basically do those things. So due to the data scarce approach, we have to be a little bit more intelligent in how we do things. Data augmentation, data synthesis, all needs to be done. To Edward's point, you can do this in dedicated areas where you have very well-refined data, where the problem statement is clearly understood and doesn't have open-ended questions. And in those areas, you already see emergence of AI, synthesis of inductors. Michael touched on it. Those are well-refined problem spaces where AI is already today helping. Chatbots enabling better interaction with the tools are being rolled out more and more. Co-pilots are emerging to help drive solutions. So this is all happening. At the same time, enhancements in the simulators are happening. You see significant speed ups. It might not be visible all the time that some of those technologies have been applied, but that's certainly happening. The bigger question of will we have an AI who can create RFIC designs in a kind of white paper approach, blue sky, blue ocean approach, where you have different technologies, different PDKs, different foundries. You just randomly pull pieces from left to right. That is a way harder problem to solve. So that will take significant longer to establish. We will start with smaller solutions, similar to what Edward mentioned, where the problem space is better refined.
Sorry, just to check on my microphone, is it now better or not?
You sound better now.
Okay, good. Maybe to make it more clear, so I have to disagree with Alex in here. So we are not limited to a certain limited topology in here. So what we really basically did is a full level circuit generation. That means building complete amplifiers from various specifications, for example, LNAs, driver circuits, power amplifiers, just based on the definition or the specification that the user wants to have. And is really exploring the design step by step, basically, in order to have, for example, an N-way combined multi-stage power amplifier, perfectly matching to the requirements that the customer or the user wants. And we have already demonstrated that in multiple tapeouts already and measured the performance actually, and also demonstrating cutting edge results already in this regards. Just recently, we've done a gallium nitride tapeout in 150 nanometer technology with millimeter wave power amplifiers, going from X band to Ka band, and reaching at, for example, 31 gigahertz and at an output power of 10 watts, up to 40 watts power added efficiency. So, which is basically really showing cutting edge results in this and design capability. And this is all not based on a, let's say, predefined topology, as Alex was stating here. So this was really a complete generation from end to end.
Just to clarify, I'm not saying predefined topology. I'm saying well-refined problem statement. And having multiple topology being explored is a well-refined problem. Having a PDK understood is a well-refined problem. Having all PDKs understood, having all available topologies understood, having all permutations and combinations of all available amplifiers in a technology, in all technologies, in all fabs understood is the big problem. So selecting one and doing it on one is, like Edward just highlighted, is emerging. That's possible. But having the flexibility of selecting different foundries, asking, can you do this now with different voltage classes? Can you do a combination, a permutation? That's where more work is needed. It's basically just the higher dimensional problem, also the multi-physics you need to run to understand those combinations and permutations. There's still some work needed.
Yeah, but
Yep.
this is actually also not a question for us anymore. So dealing with multiple foundries, we did it in silicon germanium, in CMOS, in gallium arsenide, in gallium nitride, different levels, different power levels, different frequencies from sub 6 gigahertz up to 260 gigahertz, so in the terahertz range. And yeah, for different topologies basically and different voltage levels. So sure, we have a certain limitation based on the foundry and the semiconductor and in this level, but the approach that we are following is quite universal in this sense.
But I don't think that's the point Alex was trying to make. I think he's trying to make the point that yes, we're very good at designing individual circuits, but as soon as you have that capability, AI driven or however you do it, the designer wants to do more. They want to do bigger. And now we're looking at how I include more of the system together. And now does it make sense for me, not only from a technical standpoint, but from manufacturing cost standpoint? Do I do that fronting in PA and gas, indium phosphide, GaN? Where do I do it? And how does the AI know to grab all those different PDKs, pull them together, analyze, and say, okay, I've decided that indium phosphide is going to be the best process for this particular application, giving the surrounding components and the way I think I'm going to package this. How do I trade that off? So I agree with you that yes, it's very good at doing some circuit level stuff right now. And certainly with our digital side, because on the digital side, also, as Alex was saying, I can define the problem better there because I'm using my metric as power, performance, and area. 3 very specific things that I can look at on a die. So we've had Cerebrus in industry for several years that's already designed several digital chips because it's a very focused application. You don't have the type of RF effects that you would have when you're designing things that couple and you're not just turning the device on or off. You're working sort of at a load pool or sorry, a load line situation. So those factors I think will take more time. Do I stack my die or do I put them side by side? How do I package those things? All those come into play when you're doing a complete design for a system. And I think that's what he's alluding to, that yes, we can do some baby steps on individual circuit design. That's when you start to put them together and have an overall system spec. It becomes much more complicated. Then you throw in the foundry costs, availability, and things like that. It's still going to be some very complicated problems.
On our side, our customers have a larger scope than circuit design or only RF. So most of our customers are involved with the overall system development and design. And the notion of how far are they using AI techniques already and how much reluctance they have, we see a spectrum of opinions here. One of the problems, I don't know if you have the same thing, other panelists, that customers are telling us is the notion of AI explainability. So if you have a non-AI traditional architecture base where you have multiple components and so on in a design system, if something fails and something is not working as appropriate because of the architecture and the subcomponents, you can identify where the problem is. AI native solutions seems to merge, using data, merge these boundaries of system components, and the explanation of what is failing, what is right, is it optimal for our customers become a little bit problematic. So could be generational. There is a reluctance in some of our customers on just replacing the traditional methodology, which are defined boundaries, with AI methodologies which design a whole system without boundaries. So that's what I'm trying to say, that this is the pushback we get.
Yeah, I'm totally agreeing to you that AI is some kind of merging everything, and then it is becoming difficult to identify the problems basically. But this is also that we already have in mind basically, because so we don't have like an LLM which is just predicting something or whatsoever, or we don't have an AI which is saying, okay, this would be the best and that's it. So we have basically a dual layer approach in here. So on the one side, we have a generation. And then the other side, we have a proprietary prediction method. And so on the generation side, we have like multiple layers of AI, which do the generation, trying, testing, whatsoever, and also dealing with multiple PDKs and technologies and whatsoever, and topologies. And on the other side, we have a proprietary fast full circuit prediction, basically, which is also leveraging AI models. But there we make sure that these AI models super reliant and super, basically accurate. But here, for example, we can then leverage large signal estimation much faster than compared to traditional harmonic bending simulation. So there we reach a factor of up to over 1,000 compared to the traditional factor, but still achieving high accuracy on that side. And with that approach, we basically can identify where the problems actually occur.
So if I'm not mistaken, so you have to have a traditional non-AI approach as a benchmark against how much. No, there's no need for that.
Yeah, well, like an evaluation, like traditional, but it still leverages AI in order for example, for the large signal prediction to be much faster than with the traditional approaches.
Sure.
Well, that's interesting, and that seems like that proverbial target-rich environment. So let's dig a little deeper into that, and let me merge a couple of questions together. And so I am going to sit down and design an RF circuit, and those days are long gone, as they should be. But let's assume I'm going to do that. How does AI accelerate that design, and how do you train AI for RF design? What does that look like? How is that going to enable the design engineer pulling out that clean sheet of paper?
That's a very interesting question, because let me just say, I've been in this industry a long time, and I've worked with probably almost every major electronics or commercial company you can name, as well as many military. I rarely see a designer sit down with a clean sheet of paper and say, I'm going to design something new. It's always an extension of what they've done before, and they're pulling something in, and they're starting with that already. It's very rare you see someone sit down and say, I'm going to design a PA from scratch. So in those cases, what I was talking about earlier, the ability to just move the frequency of the test bench and set that up for you and have it drop in with the new process, or even the existing process you have, or the ability to say, okay, this is my design. This particular foundry is full. I want to go recreate that same design. I want to go into another foundry, or maybe I want to have 4 or 5 foundries available. So I want 4 or 5 different designs for 4 or 5 different foundries for the exact same, to use the new buzzword, chiplet that I can drop into my system. Those things are things that we do now that can have a lot of benefit to what the designer does on a day-to-day basis. But if they do want to start completely from scratch, certainly you can. There are applications where we're doing things like that within Virtuoso, where we're looking at starting from scratch. We have the ability to not only start from a circuit topology, but we can ask it to say, generate multiple layouts for me. I'll do a family of layouts, and the designer can look at those and say, I like the way this one is. Use AI to refine this. You start looking at the couplings between the lines, do EM effects, thermal effects, and start doing some detail analysis. But a lot of times, just getting that first setup, just getting everything ready to go, building that test bench, and getting the basic circuit in play that I can start optimizing or playing with or tuning, is just a very valuable time saving.
If I may augment and add to what my friend was talking about. So many of our customers in RF design, as well as antenna and antenna array design, they're telling us that they're using the AI techniques instead of going through a full search and kind of Cartesian product of all possible test cases, they use AI techniques to prune it, meaning based on the data and based on the design initial steps, find a subset that is reasonable to test, but yet is expansive enough to give them confidence. So the notion of pruning and optimizing and kind of discarding the unnecessary test cases is something, I don't know if my friends have heard about that before. That is something that many of our customers talked about, the ability of AI to not make them do busy work for nothing. That's the idea that we hear.
And Edward, it sounds perhaps like you're in the trenches doing this. So any comments from your standpoint?
Yeah, I also can agree. I mean, you can basically do everything with AI, but also lots of non-working stuff basically. And so you really have to make sure that the algorithms and the combination of the algorithm are basically on place to serve your service and to not mess up with everything you have. I mean, as I said, I think there was also kind of research done with LLMs like ChatGPT in order to design circuits, and it turned out to be quite working at 50% of the time, but at the end this is also okay, we've got a schematic afterwards, and so now we have to put it into some kind of a circuit level simulator, or how do we do the predictions? So we definitely have to make sure that all the models that we are using, for example, definitely do their job basically, and we have to make sure that the outcomes of that are basically put in the feedback loop in order to make them reliant and reliable.
Great, thank you. So an audience question, and this one is specific for Alex and Human. Can we expect features like context-aware design suggestions, step-by-step design guidance, and natural language interface in Keysight ADS and MathWorks MATLAB in the near future? Basically something like GitHub Copilot, which assists me in optimizing design. So again, Alex, how about if you start us off with that one?
Okay. GitHub Copilot requires a prompt to write, right? So you still have the engineer asking intelligent questions. If you just go in and say, do, most likely it's not going to give you much back. So the Copilots which are in development are basically tailored to that point. It's a prompt engineering approach, if you like, where someone is asking, can you do this? Can you do this? Those things will come, and they are coming. Depending on which areas we are in, they might also result into a kind of step-by-step guidance. If you achieved one milestone and now you're asking about the next one, it will certainly help you and potentially even execute on the next milestone. So I think that's a resound yes.
Hi, on our side, MATLAB Copilot also has been requested a lot. When you are putting together a MATLAB algorithm program function, instead of just allowing context-dependent dialogue with the programmer, that is definitely in our plans, and it's been requested. So we are trying to understand and deliver on that. But the notion of context is also another optimization for us, meaning that instead of you starting to write algorithms or modify existing algorithms, and you can go through all possible mistakes you can make, the context-oriented dialogue with the software allows you to, based on what you have written so far, what you have developed so far, get the next step. And that's the foundation of what we see in LLM. It's the next logical thing. So that is something that we see appear in many companies, application areas, where based on the context you're giving me, I ask you the next logical questions. And that's definitely coming to our interface with the user in MATLAB.
Excellent. Thanks, Suman and Alex. So I kicked this off with some market forecasts. And in some ways, it seems like AI is the panacea for all the challenges in the RF industry. So what market applications and technologies do you think will make the best use of AI? And how about, Michael, we start with you with that thought.
So we're certainly seeing it in the analog RF realm, both in more traditional silicon, as well as more exotics. But we've also seen it, like I mentioned, in the digital realm. We've already deployed applications where it's having big impacts. Another area where we're seeing a lot of growth or use is Cadence was part of a DARPA program called Majestic, where we developed AI board layout to generate a board based on the size of the die, the specs, or the packages you're putting on it. Go do the routing and optimize the size or whatever. We see that being used a lot in industry already, mainly because we're starting to see fewer and fewer layout engineers. Just being able to find people have that experience and have done that type of work before is getting harder and harder. So if we can get them 95 or 99% of the way there, and one layout engineer can handle more products at once, we can vastly improve their productivity and improve their bottom line.
Great, thank you. Edward, from your standpoint, what will make the best use of AI?
So yeah, I mean, right now, as we are already doing it, so we are using AI in order to do the design generation automatically, and for sure. So as also my colleagues already mentioned, lots of the stuff relies basically on data, and data is something that we don't have in the semiconductor industry. So because no enterprise is sharing anything, circuits are not shared whatsoever. But this is where we are basically following the step that we are doing this large design explorations and pretty much faster. And I think at a certain level, when a certain model is existing, and I'm not speaking of an LLM because I don't think that LLMs, though, sure, these are good models in order to do some good interactive applications and helping in designing whatsoever, definitely. But I'm speaking of a model which is basically understanding what the physical behaviors and the RF behavior, the semiconductor itself, and how topologies are designed and how topologies react to certain combinations and so on. And once this model is established, I think definitely we will be then able for enterprises to mine through their own existing data that they have already generated within the decades. And from that mining, being able basically to build new circuits and also to adapt to new semiconductor technologies much faster than ever before, basically, because they can use existing topologies that they have done and then just simply adapt to better technologies.
Yeah, interesting. Thanks. Alex, from the Keysight, thoughts?
Yeah, maybe I just want to pick up the data thread here, since I don't think we have talked enough about it. But there's one hidden secret which most people don't talk about, is the data needs to come from somewhere, and you need to train models on the data. That doesn't come for free. That actually is very time and compute intense. Yeah, exploring those multi-dimensions and generating this stuff is just front loading your problem, right? Now you have those models who are 10,000 times faster, but they need to come from somewhere. So that's still part of the whole overall design flow. We will just see emergence of a new engineering type who will basically try to work through those problems up front and then hand off those solutions to the RF designers. And like Edward was alluding to, you need to go into companies and basically enable them to get their data sorted. And that's indeed a big problem, because a lot of companies actually don't have their data sorted. It's still secluded in different design groups. It's on different servers. It's in different time domains. So data management is one of the challenges we still have to tackle.
Yeah, totally agree with that, definitely. And this is definitely a challenge that we will need to solve in the future. But at the end, I think once this is basically done, and we can definitely leverage such kind of bigger models which can, be trained on these data.
Yeah, and maybe that's also one of the reasons why we see a little bit of a lag here. If you go into the companies, data is IP, right? They're very protective about it. There are many initiatives who've been trying to standardize interfaces, data for AI training, or even try to share this kind of stuff. Not very successfully, I would say, because it is money. IP is money. Data is money right now, and everyone is realizing that. So companies are still grasping with the new reality of getting organized around this and trying to enable those kind of solutions.
I completely agree with that. So AI as a panacea. Our customers are all learning about AI techniques, applying it. But these problems that are discussed is putting a little hesitation on the side. Number one, the existence of adequate data. And I don't know if other friends see that, the availability of generated data, meaning that the notion of if you have a digital twin, a digital representation of the system you're designing, and digital twin provides you extra data that you can test that system, that's emerging in our customers. Maybe the physical, getting data from physical reality is cumbersome, time consuming, but because you need so much data, the data can come from physical sources as well as the digital source or model of your area. See, so people are building digital twin in order to have enough data to model the AI. That's one thing. I completely agree with Alex. Standardization requires sharing, and data is definitely guarded very tightly as intellectual property, and sharing of data is a huge problem. I don't see people sharing that readily, their data which is needed. And the last problem that we see is, I told you, the data. You as a designer of AI-based system, you assert that this system is optimal and so on. How do I know? So this notion of verifying, especially for older generation of designers who are not used to AI techniques, there is a little bit of reluctance there. So these are the things that make it less panacea, my friend, is that the availability of data, the sharing of data, and the reliability of design after lots of data is used, make it less a panacea. It's a still growing field, and growing pains are there.
Yeah, maybe just adding here one more area which is kind of relevant. Since the data is so secret, a lot of people are not really leaning into cloud, and a lot of the AI applications we're seeing are all cloud-based. Send your data to someone's servers and hope for the best. We've seen plenty of hacks and leaks, which is why a lot of the AI solutions we're actually looking into are edge deployed. And that comes with a whole slew of new challenges.
Yes.
Yeah. So the way Cadence is adapting to the data problem is we've created a specific platform we call Jet AI, Joint Enterprise Data and AI Applications, that allows a company to collect their data, store it in this this container, if you will, that not only takes the data from previous designs, but it also takes the setups, the measurements, the simulations that were used, the ML or AI applications that were used. And once we have that database, this is all contained on site. We're not sending it to a cloud. You can have it all in your company. As I mentioned earlier, we have the ability to generate different layouts and designs. I can now say, based on this existing design, go build me an entire family of different designs, analyze those for me, and actually train my AI to understand what's going on with this particular type of design or system. So That obviously takes time to build, and it costs money. It costs a lot sometimes to train and do thousands and thousands of different perturbations on a particular design or a particular system. But it can be done, and as you build up that database over time, those companies that put that investment in early, I think it's going to pay off for them in the long run.
So that's interesting. Clearly, everyone's passionate about data being something that needs to be improved, as we just talked about. What else do you think needs to be improved to make AI even more helpful for RF and electronics markets? Where's that low-hanging fruit?
I think that's one interesting thing to stay on the data topic is that LLMs could help with is to ask or train an LLM to allow it to go search all these different bits of data that are in different formats or different configurations and standardize that into a standard format that can be used by your different applications. So I think there's some low-hanging fruit that will be coming in the next year or two, that you'll be able to have it organize that data for you, because engineers are notoriously bad at organizing their data.
Yeah, I would also agree to that, definitely, that LLMs will definitely, or these multi-models will definitely help on organizing data or mine data through various kind of sources, definitely. And but just in general, as it is also at the current state, for example, where's the low-hanging fruit? So basically, the component models are definitely one of the most important things, even if we are doing like manual designs, but also for AI, this will be one of the most important things, I think.
Yeah, on our side, this notion of data security is essentially covers this area, meaning, as Alex said, a lot of customers are kind of giving up on the notion of cloud. They have their edge, they have their own computers and their own data centers and don't share anything. But I think if the data security, especially on the cloud, gonna affect everything, where I guess my friend from Cadence said, you allow the customer to be on the cloud, very secure cloud, only being able to work on the company's data sets, and when they're ready to share publicly. So that notion of essentially reliability of accessing data on the cloud, where you restrict others for a while, when you do the design process, and then when you're ready, make it public. That is something that the cloud companies can help with different companies. If that problem is solved and people feel free to explore that, then the data doesn't become such a issue for development of AI applications.
Yeah, maybe just from our side, we are heavily focused on IP security and data lineage. So similar to what we heard before, there are products who are actually designed to handle those challenges, rolling those out, establishing those in the market. We have products like SOS and Hub who are designed to handle those and enable AI training to help with those kind of challenges moving forward.
That's great.
Yeah, good. Thanks, everyone, for that. A question from the audience specifically for Alex. Are there trade-offs using a data-driven black box model? Are you able to scale a transistor model? Simulate variation of devices' parasitics?
Okay, trying to understand the question. So the question is around black box models, basically data-driven models, and
scaling transistor models, simulating variations of parasitics.
So at the end of the day, it kind of now we're talking about digital twinning, right? Where does the data for the variation come from? Is that statistical variation we're getting from the fab, or is that design variations you might see in the design, which you get from simulations or synthetic data or explorations of the schematic or layout? Depending on where the data comes from, you can either use this as a data feed into your black box model, Adding statistics, of course, requires a significant amount more data to add this. We also in Keysight have approached this challenge by leaning into hybrid models, meaning we use physical-based, well-established solutions and basically augment those with neural networks to have the data-driven approach, which helps us to model artifacts we've seen now in the systems. Again, we're linking this also to our measurement side of things in Keysight when we talk about Keysight EDA. And you can do a combination of two. If you understand the model and the model is fast to simulate to also enable you, creating data, you can do either. You can stick to the physics, you can augment it through neural networks, or you can just go all plain black box depending on where your challenge lies.
Great, thank you. This next question, I think, is a really interesting one. What's the industry view on who owns the IP and design created or suggested by AI?
There are Supreme Court's questions right here.
Exactly.
Multiple
layers, that question.
Yeah, frankly, that's a copyright question indeed. And for those of you who actually read into the copyright, we'll see that there are certain limitations to this question. I can give you a quick interpretation of how far I got. If a monkey draws a picture, who owns the picture? And the short answer is animals and non-human beings are not covered by copyright.
Mm-hmm.
Yeah. So what that means is a human needs to be in the mix to touch the system, or else you don't own the IP.
Yeah.
That's how the current copyright laws are written, and everything else is in the courts to figure out. So I think we have to watch and see.
Yeah, I think much more to follow on that, and I think that's a good, succinct way to sum it all up. So thank you for that. So we are a wireless world, and I think I get in trouble if I don't mention 6G in this wireless world these days. So how will AI shape the future of 6G and beyond in RF technology?
I've been going to many conferences about 6G. That's one of my responsibilities at MathWorks. And what I hear a lot in the 6G context is the word AI native, meaning that you want to bring AI applications natively as part of the wireless system design. Again, I mentioned to you the three classes of problems that everybody has been struggling with are multivariate problems, nonlinear problems, and problems with exorbitant complexity. For example, in 5G system design, the number of parameters at the physical layer that can affect the signal that you're transmitting from one node to the other node, there are so many of them that the schedulers designed by wireless engineers to actually set those parameters use a small portion of that. So 6G is trying to bring this notion of optimization brought by AI to the resource allocation. This is very, very important. I think Edward mentioned orchestration. That is a lot discussed, is that based on the data we get constantly in real time, the integrated sensing and communication, all the data that we have available, can we then use AI techniques to optimize the allocation for the user? That is one application. And so this notion of optimizing resource allocation using AI techniques used a lot. And then other techniques that rely on AI are used in the context. Many applications of 6G require AI, but this notion of optimizing resource allocation is my favorite one, because the number of parameters are too big for any algorithm written by any of us can handle that. So AI will learn gradually and optimize the situation as it arises.
Yeah,
So
I would add here maybe to Oman. Sorry, 6G. They're trying to identify the protocols and how the systems will communicate, right? So we talking about a decade out or something.
Not defined yet. These are ideas that are being discussed. So
Yeah.
nothing is written down.
But basically, what we know is the data which will be going through those channels will be tremendous, and there will be just so much more interference which needs to be handled. So neural networks are designed into the receivers and transmitters in 6G to basically manage those systems and that complexity which we will see coming out of it. So that's where AI will sit. It will sit right in the hardware to do all kind of dynamic reconfiguration and adaptation to establish proper, beamforms and signal communications and things like that.
So very interesting that discussion around the 6G, because a lot of what you're talking about in resource allocation has been demonstrated. And at Mobile World in 2019, there was a Spectrum Collaboration Challenge that DARPA sponsored, and different teams put together a scenario where you have some natural disaster and you have fire, police, rescue, many different agencies involved, and they all want to use the bandwidth. And the challenge that DARPA put to the different teams was, you want to optimize communication, but you can't do it just for one group. You have to be able to optimize it for everyone. And you can find this presentation on YouTube. It was like an hour demonstration of how they went through different metrics on how the different teams were communicating with one another, and how they optimize the overall effect of the system, not just their own application. So this has been demonstrated, and yes, I think this would be a big important factor for 6G and how we allocate the resources, because you're talking about tremendous amounts of data and tremendous amounts of capability, and how do you allocate that as efficiently as possible? It's going to be a big application there.
Alex, any thoughts on this?
No, I think you kind of summarized it well. So Keysight is trying to drive 6G protocols and definitions, and there are some interesting things, maybe just on the side. Today, when you talk about signals and signals beams forming and communicating between two devices, we normally think about straight lines, right? Line of sight, if you like. Since AI can also think multidimensional beyond what we can put an algorithm, to Homan's point, we're also seeing things emerging like just bouncing off signals off walls and, playing ping pong along those lines just to establish communications, which you haven't seen before. So there are interesting, things we can do with having AI embedded into those systems and driving intelligent decisions.
Yeah, just want to augment on that. So this notion of 3D scenario modeling, which what you're referring to, which is, the direct line of sight is one thing, but reflection, especially in the high dense urban area, the technologies that are being discussed for 6G are essentially have been proven in laboratory, but not at a large scale. Like this notion of reconfigurable intelligent services. If you are in a large scale urban area and these blockages provided by these large buildings, can you essentially bend the signal around edges using reconfigurability or changing the reflection patterns? That is RIS, or reconfigurable intelligent service, discussed as 6G. This notion of integrated sensing and communication, everybody is writing about that. These are technologies that are discussed on 6G. The notion that a base station can join the operations of communication with operation of sensing. When it's not communicating, using the same hardware, same frequency, same bandwidth, sense the environment, and use that sensing information to feed it back, and in the communication optimize the beamformers, the bandwidth usage, and all of that, as Alex mentioned, all of that requires an engine, an AI engine that orchestrates that. And these technologies that are being called 6G technologies will require an AI essentially master to orchestrate all of that.
And so that's excellent. Thank you all for that. But unfortunately, we are out of time. So I'd like to thank the panelists once again for a great discussion. I hope everyone found this as useful as I did.